chat, but we will keep that until the end of the content. Yeah, Pablo, over to you. Thank you.
Okay, great. Thank you very much, Sophie. As Sophie said, this week's topic is continuity models, which is a core part of any mobile phone data analysis pipeline. My name, as she said, is Pablo Ruiz, and I've been working at Nomon for over 6 years already, where most of the work that I did was related to actually working with mobile phone data, and a lot of it was related to continuity models. So I will try to share my expertise and our expertise at Nomon in how to design, how to build a continuity model for a mobile phone data analysis pipeline, and also a bit on what are the, let's say, best practices of the field. So the structure of the session is very similar to the one from last week. So for most of the session, like 40 minutes more or less, we'll go through some slides in which I will try to share a bit on what a continuity model is, how some key ideas on how to properly implement it, and at the end of the session, well, there's a practical exercise for after the session for your own time, like a self-led coding exercise that I will introduce in the last 10 minutes of the call, and then we will have the Q&A as Sophie introduced. So first of all, we have to answer the question of what is a continuity model. The basic definition that we're working with for what the continuity model is a sequence of algorithms or rules, if you'd like, to identify some continuity states from each user's individual events. So here we're working with events data, individual, disaggregated user events data. And what the continuity model is, basically, is something, some module, some set of rules that for each user identifies or tags where it's in each of the continuity states, right? So now we need to define, of course, what a continuity state is, right? So the basic continuity states that we work with in mobile phone data mostly are just stay or move, okay? So a continuity state of a user just describes if a person is either moving or it's staying still at a certain place. The exact definition of what moving and staying still depends a lot on the use case, but as a general rule, these are the two main states. So continuity model, just as a recap, we have the user events from the mobile phone data. We feed them into the continuity model, and what the continuity model outputs is this inferred continuity states. So it's something that tells us from this time to this time, the user is staying at this location. From this time to this time, the user is moving. From this time to this time, the user is staying at this other location, and so on. And we can run this for any period of time that we want. Typically, we can do it for a day. We can do it for a month, for a week, anything like that. So why do we need continuity models in mobile phone data analysis? Well, for 99% of the use cases in which we work with mobile phone data, we actually need to know when the users are actually staying at the place and where the users are just moving, right? So for example, for travel and commuting use cases, it's key to identify properly when the users are still, because some of the key or the main indicators that we produce for travel and commuting are, for example, all the matrices, in which it's key to identify the origin and the destinations of these trips, right? For trip statistics. For tourism, it's also very important to differentiate between visitors that are staying at some specific places and others that are just passing by. And for disaster management, of course, for example, for epidemic control. So it's also very, very important to know just when or get statistics about where people actually stay for a meaningful amount of time, and when people are just like presenting events at some places, but they're just like moving, so they haven't stayed there for a significant amount of time, right? So with this introduction, maybe some of you might think that this sounds relatively easy, right? So we have the user events. We just have to say when the user is staying at a certain place and when they're moving, right? But the challenge is that actually it's not as easy as thinking, okay, when the user is connecting to a cell and it's connecting to the same cell, then they're staying at the same place. And when the user changes cell in their events data, then they're moving, right? So making that assumption actually would lead to a harsh overestimation of movement, because, and we'll see that in detail, in a bit more detail afterwards, actually switching connection from cell to cell, that does not mean that the user is moving, right? And even having the same event, having two events in the same cell in maybe 2 minutes or 3 minutes difference, for example, does not mean actually that the user is still, right? Because the coverage area of the cells is large, so it can be somebody that is moving through the coverage area of the same cell, right? So we have to, the continuity model, we have to build something that is able to, with these noisy user events, with cell connections, changes, and so on, we need to infer correctly when the user is staying at the same place when they are moving, right? So these are, now I will try to share or to try to make you understand what can be the consequences of an oversimplified continuity model like the one I said before. So if we assume that the person, that the user is moving every time they change cell connection, the statistics that we get at the end are not really reliable, right? So right now we will have a poll, just a quick poll. It's a very easy question, and here at this slide we can see two graphs, right? One graph, one of them presents both of them actually contain the same information, which is the number of trips that we have calculated with a continuity model depending on the hour of the day. So it's the hourly profile of trips in a specific city. But each of them have been calculated with a different continuity model, right? So the question is, which one of these do you think has been calculated with a, let's say, solid or robust complex continuity model? And which of them has been calculated assuming that every cell change, right? So every connection change is actually a move. So I will leave maybe 15 seconds for you to answer, either A or B. Okay, so I think I can. Okay, so I can read the poll question out loud. The poll question says, which of these graphs do you think results from an oversimplified continuity model that flags every cell change as a move? So either it's A or B, right? The one to the left, the blue one, or the red one. Okay, so the truth is that the continuity model that was calculated with an oversimplified, the graph that was calculated with an oversimplified continuity model is the one to the right. Okay, typically the trips that we have in a city are much lower at night than at like morning peaks and evening peaks and so on. So this is like the typical trip hourly profile that we will get from from a reliable, a robust continuity model. But what we get often in with like a naive continuity model that treats every cell change as a move is an overestimation of moves. So we get more moves here to the right than to the left. And actually we get like this kind of base noise of moves that actually makes us overestimate, especially the trips at night, right? So this is one of the consequences that it can have to have an oversimplified continuity model. Another consequence that it can have is that, of course, we might end up, for example, in this case, overestimating the stays, the amount of time that people stay in places where people are just producing events due to movements, right? So here we can see a capture of in this case, the city of Madrid. Okay, And we can see a lot of registers. It's a kind of like a heat map in the main arteries, like in the main roads of the city. But this is not where actually people stay most of the time, right? So this would be more of like a real heat map of the real visited place, right? Produced with a robust continuity model. So up to this point, I hope I convinced you that it's important to build a good continuity model that works for our mobile phone data pipeline. And in order for you to understand more or less what continuity model needs to do, what I've done, what we're going to do is let's play continuity model, right? So we're going to analyze the events, the cell connections of one user, of one device, which are just here, okay? These are the connections of one device during one day. The device starts here and moves down, and then we'll see exactly what it does. And we have a video of these connections, right? So here we can see the time down here. So it's a user that clearly at night staying more or less at the same place, right? We can see how in some cases the cell to which it connects is not exactly the same, right? We're representing these points by the cell locations, but that doesn't actually mean it's they are moving, right? It's just the cell connection might change because the coverage areas actually overlap, right? So we see how the user is more or less at the same time, at the same place, sorry. It's already 8 a.m., 9 a.m., and the user is at the same place. And then clearly the user is moving. Now it looks like the user is staying more or less still at the same place, right? We can see now some kind of move, but actually quite small. And we can see that it looks like the user ends their day, right, at night, at the same place where they started, right? So a way of, let's say, visualizing this information that is very useful, and we'll see this in the following slides also, is to plot this sequence of registers instead of just in a 2D plane like here, actually in a 3D plane, right? So we have like the XY plane. So here we have the spatial dimensions, let's say, but we add the time dimension to the z-axis. Okay, so here we can see how actually the user, like the time starts here. So what we've seen, right? The user stays still at the same location for a while, then they start moving. Then it looks like they stay still for another time, right? Like it looks like from 11 to 20, for example, more or less. Then the user is moving again, and then the user ends their day at the same place where they started, right? So their XY coordinates are similar. The only thing that changes here is time, right? So this is a very good way of visualizing this kind of information, and it will be useful for also the next slide, right? So here we have another poll, and as I said, let's play continuity model, right? So one of the things that continuity model has to do is to guess correctly the number of stays that the user has performed during this day, right? The number of stays and the number of moves. So the question of the poll that we have right now is how many different stays would you estimate that this user has performed during the analyzed date, right? So this user during the whole day, how many stays do you think it has, like a continuity model would assign to it, or would you think that this user, how many stays does it have, right? So I will leave the events again. And you can answer with just the number in the chat, right? So you think maybe it's 3 stays or 4 stays or 5 stays, so you can answer with one of those numbers, right? So we see how the user clearly at the beginning is staying at one place, but afterwards it's doing different movements, right? So I will play the video again. So this is one state here. Then when the user arrives, because they're clearly moving, they're performing another stay around here. Okay, I can start to see some answers which look right. And then there's for sure there's a last stay here, right? So we have at least two stays, the one at the beginning and the one at the end, this one and this one, and some in the middle. So I'll just put the video one last time, and then we can see the answer. By the way, these are data that are synthetically generated to look like real data from real users, right? But this is more or less what the events of one user might look like in the mobile phone data. Okay, so let's go to the next slide. The answer actually is not obvious, right? We kind of saw at this part of the day, we kind of saw one place where the user looked like they were staying at the same place, so right here, and then they kind of maybe moved for a bit, but not so clearly, and then they moved a bit more, right? So we might have there like here just a small stay, or maybe it was just all part of a move. That's different. Actually, that's difficult to tell just from the mobile phone data records. Sometimes they have like this granularity that when we go like to a very minute detail, let's say, sometimes we're not able to tell. But any answer that's between 3 and 4 stays is correct, right? Because this person clearly is doing a long stay here, long stay here, long stay here, and then here in between, it's just between 3 and 4. So actually, all answers were correct. So now it looks like we're able to actually be the continuity model ourselves, but now what we have to do is to make some algorithms that are able to do exactly this automatically and with all the users, right? Okay, so let's assume that we have decided that this is 4 stays instead of 3. So the stays are at these locations. This is something that actually needs to be, it's part of the output, let's say, of the continuity model. So the continuity model classifies the users in their final output in this way, right? So they classify the users are either they're staying at the same place, they're moving, they're staying, moving, and so on. So if we have detected these first 4 stays, which correspond to 1, 2, 3, and 4, then the rest of the time correspond to this, let's say, horizontal in this graph, horizontal moves, right? And this is what actually we intend to obtain from a continuity model, right? So staying at this location, moving, staying at this location, moving, staying at this location, moving, and so on. Okay, so before starting with the exact algorithms for the implementation of the continuity models, there's some initial considerations that we have to keep in mind. The first one, like the main one, is that for mobile phone data in general and for continuity models, specifically, there is no one size fits all. Okay, so we may find a lot of differences, many differences between mobile phone data analysis, and it's not just the data provider, but that's true too. That depending on the data provider, the data we're analyzing, it might have more event granularity, it might have more information, more data fields, less data fields. So that's something that we need to account for when designing a continuity model for sure. But even within the same raw data, within data provided by the same provider, we have many devices that generate, we have devices that generate many events, but we have other devices that generate very few events, right? And also, we have big differences in antenna density, in antenna sparsity, right? So in urban areas, we have lots of antennas, lots of cells, while in rural areas, we have fewer of them. So we need to design a continuity model that actually works for all of this, right? That works for devices with many events, for devices with fewer events, and for devices that are in urban areas and devices that are in rural areas. So we have to take this into consideration, not to introduce some bias into the results, right? The exercise that we'll do, we will work with a, let's say, simple continuity model, but with a in more complex continuity models, we need to introduce this into the equation. Okay, and then there's a final, let's say, way in which the mobile phone data analysis can be very different, and that's the use case, right? So depending on the use case that we're for which we're doing the continuity model, the actual definition of what a state is changes, okay, and the required precision changes too. Okay, so for example, for commuting, we need more detail, more precision, because we need to identify like short, maybe trips from home to work, right? And for migration, we need less precision, because we just want to know some statistics of people that were living in some specific location and moved to some other, right? Just as an example, so what this stays, so home, work, groceries, and so on, would be the ones for a use case about transport and commuting. But for some other study like interurban transport or, as I said, displacements, migration, we might actually want to consider all of this just as the same stay and all of this just as a big stay, right? So this is something that, of course, it's important to define the actual continuity model. So for all these reasons, the continuity model, like a perfect continuity model, needs to be flexible, okay? And flexible in a sense, in the specific sense that an ideal continuity model should be first configurable, so that when we have different data sources, different use cases, or different scopes of the use cases and so on, we can actually tweak, we can actually modify some parameters, some thresholds, spatial and temporal thresholds. We'll see later which ones this can be, so that it can work accurately, like I said, with different data sources, use cases, and so on. And also, an ideal continuity model should be adaptive, right? So within the same data source, within the same use case, it needs to treat, let's say, some devices in some areas a bit differently, so that their results, both, for example, in urban areas and in rural areas and across devices, are actually reliable, right? So this is more or less the basic, like the key elements of how a continuity model should be. And in order to check that the continuity model is working, any continuity model, it's essential to ensure that it actually captures the real movement patterns of the users, so that it's working correctly, right? So to achieve this, to validate the continuity model, we can use either user-level reported mobility. So in some cases, maybe some users can voluntarily agree to share their movements through survey or apps, and we can compare the actual real movements to the movements that are detected by the continuity model. So that's a way to validate and calibrate the model and fix the ways in which the continuity model is not working properly. But we can also achieve it by just visual inspection, like we did in the video, actually. So the continuity model is saying the same thing as I would say with this event. So that's a good clue. And we can actually use external data sources to compare aggregated data, right? So if we have some, for example, survey statistics or travel survey statistics, we can compare it to the number of moves that we get, or to the average number of moves that we get per user for different types of days, for example, in order to find out if the final statistics are compatible with the ones that we're producing, right? Okay, so now let's get into continuity models implementation. So the actual methodology for implementing a continuity model, right? The way we work with continuity models, and something that's very common also in the literature, is that there's one initial step named cell bounds cleaning that precedes the continuity model core algorithms, let's say, that are the ones that decide if something is a stay or something is a move. And this cell bounds cleaning part is optional, so it's not strictly needed, but it's something that helps clean the events, so the continuity model core actually works much better, right? So we're going to explain a bit what this cell bounce cleaning consists of. Okay, because it's it's highly recommendable to use it within the continuity model for it to work properly and not overestimate events. Okay, so by doing this cell bounce cleaning, what we our objective is to fix this cell bouncing problem. So as we've said, there are cells or mobile phone towers that share coverage area with others, right? So here, cell B has a coverage area that's completely overlapped with cell C. Some user can stay here with their device, and they can connect first to B, then to C, then back to B, and so on, right? The key thing here is that a cell change does not necessarily indicate that the user has moved. It just means that the user has switched cells. That can be due to network conditions. So maybe some antenna was more busy than the other, or signal strength, which changed, and so on. So the fact is that we have this situation, like this phenomenon really often in mobile phone data, where users may appear to bounce between neighboring cells, right? So if we see the events, so like the ones we saw here, we see how for some time it looks like the user is at the same place, but they're like bouncing between these different locations, right? So they are at the same place, but they're connecting to cell B, to cell C, to cell B, to cell C, and so on, right? This doesn't mean that the user is moving all the time. And if we can clean this cell bouncing before actually applying the continuity model, we will actually get rid of a lot of noise, which might actually impact the results, right? So as I said, this is optional, and there are many possible approaches. But we'll see a simple but effective method. That's the one also that we are implementing in the exercise, in the notebook example, which just consists of if we have a quick switch between neighboring cells, so we connect to cell A, then B, then back to A, in, for example, less than 30 minutes, then we can assume that for sure is, or almost for sure is, a cell bounce. And if it's not, well, since in the mobile phone data we don't have that much granularity to detect if that's actually a move or not, we can, let's say, stay at the safety side and assume that they're just staying at cell A, right? So if a user connects to cell A, then to other cells, and then back to A within less than 30 minutes, what we can do is just assume that the user is staying at cell A. So we can replace the events at other cells by, let's say, synthetic events at A also, right? And this is the information that then we can feed to the actual continuity model. So by doing that, we kind of have a bit of noise here. For example, the user is switching cells. We can, the events that we're modifying are the ones in red. We can get something that's much cleaner, right? In which it looks like there's more continuity in the place where the user is. And this is, let's say, better data to input to a continuity model. So this is just a cleaning, let's say pre-processing, if you'd like, of the events data for the continuity models. And now we'll see the actual core part of a continuity model, how it can be, okay? There are two main approaches, let's say, two general approaches to state move differentiation, so to continuity models that you see in practice, in commercial projects, and also in the literature. There are some methods that are more speed-based. So what they do is mostly they calculate speeds between different events. Okay, so you're in one cell, then you're in another, so you calculate the distance and the time difference, and you calculate some speeds. And with some threshold, you determine that some things are moves, some things are stays. Okay, so those are the speed-based approaches. This is the example that we will see more in detail, and it's the one that it's also in the practical exercise in the notebook. And we have also clustering-based approaches for continuity models, right? The clustering-based approaches are a bit different. We will just see a few key ideas, but basically what they do is they group together events that are very numerous, let's say. So we will have many events at the same location during the same time. Those events are clustered, they're grouped together. and that's the way it detects the stays. And then the rest of the events are just moves, okay? So let's get into the speed-based, okay, continuity models. So here the key idea is we have the event sequences of the user. So what we need to do is to compare the speeds between these event sequences to some speed threshold. And when the speed exceeds the speed threshold, for example, 10 kilometers per hour, then we can determine that that's a movement of the user, okay? So these thresholds, as I said, ideally, they should be configurable and adaptable. So they should be flexible for different devices, for different areas, okay? But again, in the example, we're working with fixed thresholds just because it's simpler and it's a foundations course. And yeah, here I've put a link to a document of the multi-MNO project for Eurostat that it was mentioned also in other sessions, in which there's a continuity model also that actually works with three cell event sequences. Okay, so what it does is to for each three different cells sequences of the user. So they connect to cell A1, then A2, then A3. They calculate the speeds from A1 to A2, from A1 to A3, and from A2 to A3. And whenever some of these speeds exceed some thresholds, then they determine that the A1, A2, A3 part of the events of the user corresponds to a move, right? It's a bit more complex than that, but you can see a bit more of this in the link. So the approach that we will take for the practical exercise consists on just calculating speeds between sequences of two events, okay? So what we're doing is calculating the difference between the first event at the given cell A and the first event at the next cell B, okay? So the user is changing location, we calculate the distances between these cells, and we calculate the time difference between these events. And with that, we can calculate some speed, right? And if we do this for all event sequences of the user, we can actually make a plot of the events as we had it before with the time in the z-axis, but actually now we have all the events colored by their speed, okay, by their calculated speed, calculated in that way. So we can see already that the parts that we're classifying as stays, so this initial part and this final part that were definitely stays, and even this part here and this part here have much lower speeds, right? We have the legend here. We can see how very low speeds, so 0 kilometers per hour, is this kind of dark blue purple, and we have higher speeds are more greenish and yellow. Okay, so by doing this, well, we can also see the results in a graph like this. We have found that during the day, so these are the 24 hours of the day, and there are events with, in the y-axis we have like the speed. There are events that have higher speeds and that are concentrated in time, right? So here we can see very clearly how we have these peaks that look like they correspond to the actual moves, to this part, and actually this small part here, which we weren't sure if it's a move or not. Here we can see also that it's a small, it's a bit above 0, so it's some speed, but it's a low speed actually, right? So what we do now is place some speed threshold and say that everything above this speed is actually a move, and everything below this speed is a stay, right? This is just a simple approach, but it can work for a simple continuity model. And the way we do here, we can choose the different speed thresholds depending on the use case, on the area, and so on. Here, what we do normally is that if we have super short moves or super short stays between moves, those stays and moves are often absorbed by the bigger stays and moves that surround them, let's say. So if we have here just like this small peak and it was above the threshold, since it's super small and very short, then we would probably disregard this as being just a stay, part of the stay as it is now, and not actually a move. And then we have classified moves. We have detected moves like this. So the rest of the day, the user is just staying still at the same location. So by doing this, we have found that the user has, in this case, 4 stays. So either 3 or 4, we said that it worked for us. Actually, by now, the remaining part of the job of the continuity model is just to decide which is the location of each of the stays, right? Because we need to know the user is around this location, moving, then this location, and so on. So what can be done normally, like a simple approach, can be to do just the centroid of the events that are related to the stay. So here we have, for example, these 4 events that we have classified as a stay. We can do the centroid of the locations of these 4 events. We can do it weighted, for example, so that if we have 3 events in one location and 1 in another, this location, let's say, is given more importance than the other. But by doing this, we decide on a specific location for each of the stays. And yeah, by doing this, we end up with the results that we were seeing at the beginning, right? So as a user, like the whole day of the user mapped to either stays or moves. Okay, so those are speed-based approaches for continuity model core part, let's say. And we'll see a bit on how could we explore also clustering-based approaches. Okay, so first of all, in case for those of you who might not know, clustering is a machine learning technique that what it does is just it groups data points into natural groups, natural splits or clusters, okay, based on their similarity, so that elements in one cluster, elements belonging to one group, are more similar to the elements in that same group than to all of the other elements, right? So a typical example is to have these data points in, for example, in space in X and Y dimensions, and what clustering algorithm does here is it finds, let's say, places where we have like high density of data points, and then we group those together, right? So we have this data that is not classified at the beginning, and by doing this clustering analysis, we classify in a same cluster those points that are actually close according to the data, right? So right here we might find cluster 1 that has all these points, cluster 2 with all these points, cluster 3 with these points, and then some clustering algorithms also leave out outliers, right? So we have points that are actually far away from most of the other points. We don't just assign them to some of the clusters. It looks like actually they're quite different from these points, right? So we leave it out as outliers. So the key idea of the clustering-based approaches is to use these clustering algorithms to cluster events according to their location and time, okay? So when we cluster events, those events that are clustered together, so in this example, would correspond to stays, and these kind of outliers in which the users don't spend much time, just they pass by, those are tagged as moves, okay? So there are lots of types of implementations of clustering-based approaches for mobile phone data. One of the most common is using DB-scan clustering, which is density-based spatial clustering. What these algorithms do is this part here to the left, right? So it's very similar to what we were doing in the previous slide in this part, clustering data according to XY dimensions. So if we look at the events that we had for this user before, what this clustering algorithm does is find places where there's high density of these points, right, of these events. And if we have high density of these events, then we decide that those are clusters, and the rest of the events correspond to outliers, right? So those would be classified as moves. And this we're doing without taking into consideration the time dimension, right? But if we look also at the time dimension, we see that actually a place where we had a cluster has this clear discontinuity, right? So these events were all clustered together, but since it's clear that there's different stays between this part and this part, then they're classified as different states, right? So we cluster first, then we do this kind of post-process, taking into consideration the time variable also, the time dimension, and we end up with actually pretty similar result than the one we had before, right? One state here, another here, and a different one here. So for more details, I'm leaving some links in many parts of the presentation. Then we also have another implementation example, which is the sliding window clustering. So in this case, we just start. This is not, let's say, a formal clustering algorithm, but it works in the same way as clustering, and it's very common also, very commonly used. So what we do here is start at the first event, and as long as all the next events are relatively close to this first one, they're grouped together. And as soon as there's one that is too far away, then that one is not grouped together, and then the cluster is closed. Okay, so this way we close this cluster. Then for the next event, we try to do a cluster, but since the next event is too far, then we don't cluster any events until this point when we cluster all this together, and all this together. And again, some examples of implementations here in the scikit mobility library, which is very useful for mobility analysis, and then in an academic paper also. So finally, by implementing either speed-based or clustering-based continuity models, we get pretty similar results, right? So we might see that there's a few differences, like for example, this state 2, the speed-based model is saying that it starts kind of a bit earlier than the clustering-based model, and it says also that it ends a bit earlier, and the clustering model, it says that it ends a bit later, right? So here there can be like few slight differences between results of different continuity models, but if they are, let's say, solid or robust, they would always agree in the most easy things to see, right, from the beginning. So, for example, these states, they have to be detected by any correct or robust continuity model. But these parts, well, there's always this uncertainty with mobile phone data, and we're not actually sure if the user was still at the same place from this time or not, or if the stay was a bit longer. So here I've put some reading material for a few more advanced topics that we didn't have time to go through in the presentation. Just in case you're interested in this, just a few methods to determine the exact start and end time of each move state, which we haven't talked about a lot. How to disaggregate, for example, states and stops into activities, tour sequence inference, spatial cell awareness, like using some special cells like antennas that are at roads or in metro stations and so on, to actually infer that those people are moving, because we know that when people are producing events in different metro stations, they are for sure moving. So there are some links also here. And we've seen only actually to this point continuity models that work, let's say, for domestic stay and move analysis, but we can actually also introduce abroad trips, abroad moves, abroad stays, okay? Because even if we have roaming out data, or if we don't have it, there are ways in which we can infer these movements to other countries, okay? And this is, let's say, the end of this main part of the presentation. Right now, I will try to introduce the practical exercise that we're proposing here. So the practical exercise is in the same GitHub repository than the one for the last session, for the input data quality assurance and cleaning. So you can just click on the link and give me a second. Yeah, and access the GitHub repository, and within the GitHub repository you have the continuity models coding exercise that you can just click here to open in Google Colab. Okay. So here I will, okay, I'm already connected to the notebook. This is good. So here there's like a short overview of what this exercise is, or what this notebook contains. The actual exercise part is just the last part, which we will see later. But the notebook contains a lot of things before that, right? So the notebook is structured into 3 sections. Oops, sorry. The first one is just loading the libraries and the input data, which is stored in the GitHub repository, so that you can actually use that to run the continuity model. This part is just this one here. So I will start to run in the first cells, just so you can see how it actually loads the data, right? So here we're loading the cell's data frame with the information, the location of each cell. So this cell ID has this longitude and latitude. And here we're loading the events data, right? So this user at this time had an event at this ID. So this is just the first part, just loading the basic things. It should work correctly just as it is. Then we have the second part, which is the continuity model example. This is the part where actually there's the definition of the functions that build each of the parts of the continuity model. So we have, for example, the cell bouncing cleaning that we saw before. So we have a function for that, a function for speed calculation, and so on. And what we're doing in this example is applying these functions to the events of just one user, right? So you've seen the examples in the presentation of these maps or these visualizations that we're seeing. So we will apply each part of the continuity model to the events of that user, so that you can understand what it's actually doing. Okay, so that's contained in step 2, and you can go through that just to understand what each step does exactly. And then in the final step, just there's the actual exercise, right? So the hands-on task that is proposed to complete. So we'll go through the continuity model example just very quickly, so that I can just share a bit of the structure, and so that you can understand what each thing does when you actually do the exercise. And then I'll read the exercise, so that you can also ask any questions if you have any doubts in a few minutes. Okay, so this is the continuity model example. First of all, we have loaded the whole events data set in the cells above this one. And this events dataset has events of, I believe it's more than 1,000 users. So for the example, we're just selecting the events of one user. So we've picked the events of user 3 on day 3, for example. And by doing this, by running this cell, we can just select the events from that user. Then we have these visualization functions that you can also use to visualize the events of the users. So here you can change the user, you can select any other user, load the data frame, the events data frame from that user, which is already loaded, and then you can actually visualize it here, right? So this is the same style of video that we were seeing in the session. This is where I recorded it from. Okay, so we can actually see how the events of the user take place. Then we can actually also plot the visualization of the trajectories. These ones we've already seen them, so you should be able to also do this and analyze the events of any of the users in the data set. And this is just actually selecting the events from the target user for the example. And then we have the definition. So anytime you see the brain here and the function definition, this is the definition of the functions that actually do the work. Okay, you don't need to see this in detail. What this function does is explained here in its section. But if you also want to analyze it to see how it's built, you can actually do it. And then here's where the processing is actually done, right? So we run the function cell just to define it. Then we can actually process the raw data frame that we had generated to get the clean data frame, and then we can see the results, right? So we can plot the results again. And here we see the example that we were seeing before, where we were actually cleaning the cell bouncing from the events of the user. And we can do this for whichever user we want. Then we have some other functions. Okay, this is just to add the coordinates to the events data set. So basically, in the original events data set, we only have these 3 fields, but we want to add actually the X and Y coordinates in order to be able to calculate speed later on. So this is just that function. It's quite simple. This is, and again, it's explained all here. This is the way that we calculate the speeds for each, for each event. So we can just define the function, just apply it, see how for example, the 3 first rows of the output of this function look like, and even plot it, right? Like it's in the graphs that we've seen in the presentation. Plot it also in 3D, where we can see each event with the speed of each event and the timestamp and so on. Okay. Then we can this part of the notebook, again, function definition, is the one that actually applies these thresholds that we have, high speed and low speed thresholds, in order to classify events either in stays or in moves. So just again, run the cell, and we have an additional column that tells us if each event is related to a stay or if it's a move. We have this. We can actually also visualize this. So stays here in blue, moves are in red. It looks like it's similar to the results that we got in the presentation. And finally, this is the last function, okay, from which we get the final continuity states data frame, right? This would be the results from our analysis. And here we just, yeah, as I said, we just have like the whole day of the user classified either in a stay or a move, each with its start time and end time, right? So here we're saying that this user has 4 stays, right? As we were seeing. So this is just the final part. This is the part where we define what the practical exercise is. So it's explained here, but basically what you need to do is to select, to use these functions that are defined in the cells above for each of the steps that are needed to apply the actual complete continuity model. We also define the parameters that you need to use for each of the steps. So as we said, we have to define the speed thresholds and the processing time, the threshold for filtering, for cleaning cell bouncing. And with these functions, you have to just place them here in these cells. We have, in this case, we have 2 cells, okay? So we can place them first one in the first cell in order to actually apply the continuity model, but not just to one user, as we were doing it in the example, but to the whole set of users, okay? And if you just fill in the gaps as the exercise proposes, then this code, what it does, it said that it should just plot a summary of the results, okay? So here we just need to fill in the gaps with the functions that are defined above and the target events data frame. So the whole data frame with the whole events. And if we do it correctly and we run the cell, it might take a while. So in different runs, it's taken me like 15 to 25 minutes because it's a lot of events actually. But at the end, it should generate actually a graph with the number of average daily moves by user depending on the weekday. Okay, so we would see Monday, Tuesday, Wednesday, Thursday, and so on, and then the average number of trips. And then the second part of the exercise that is proposed here is doing exactly the same as in the first cell, but actually skipping the cell bounce cleaning step, right? So this step that goes before the continuity model core, let's say, so not using the clean cell bouncing function, so that you can see how it actually affects, how it would affect the impact that would have to the final results, not actually applying this preprocessing, okay? So I don't know if I say it at the beginning, but at the end, for this session, there's also a quiz that you need to complete for the course completion. It's very simple questions, just 6 questions that you should be able to answer from this webinar, and also you will have access to the presentation. But 2 of those questions, the last 2, are related to the results that you get here, right? So some of those questions will ask you how these results that are plotted here look like. So yeah, this is the practical exercise, and that's all from my side, I guess, until the question and answer part, which I'll be happy to answer any questions that you have now.
Right, thank you so much, Pablo. Thank you so much, everyone, and I hope to see as many of you next week. And Pablo, thanks again so much for the training today. And I wish you all a great week. All right, thank you. Bye.
Thank you.